So hello everyone, and welcome back to Solid State Physics in a Nutshell, brought to you by the Physics Department at the Colorado School of Mines. I'm Eric.
And I'm Nicole.
So far, Nicole, you and I have explored covalent bonding, but there are of course other type of bonds that exist. Today we're going to introduce two general categories of bonding, the first being metallic bonds, and the second, intermolecular forces such as van der Waals and hydrogen bonding, and look at what drives these interactions.
Metallic bonding is so neat that we'll spend a whole chapter on it later, but for now we'll cover a simple description of it. And if we look at a chunk of metal, we'll see a bunch of atomic nuclei with the electrons dispersed like a negatively charged seed throughout the material.
Exactly, and what's nice here, looking back at quantum and thinking about particle in a box, we treated the electrons in the box as a gas. It turns out that metals are a great system to apply the particle in a box model to.
Okay, I can see how these electrons are spread throughout the material. But what about the nuclei? Are they stuck in their positions?
Actually, that's what's surprising, is that in metallic bonding, there is no inherent requirement for periodicity. Let's think about gallium. Hold it in your hand, turns into a liquid. Here, the positively charged nuclei are moving in all sorts of random directions, but the electrons still form the sea that moves between the nuclei.
Can we observe this experimentally?
Indeed we can. So let's pull up some electrical conductivity measurements across the solid-liquid phase transition for gallium. We can see here that while the electrical conductivity drops as gallium becomes a liquid, it doesn't drop by that much.
So in essence, we can still treat them as delocalized and free to move around. So metallic bonding is not really a bond when one normally thinks of a bond. Instead, it seems to be a balance between attractive and repulsive Coulombic forces.
Yeah, so now that we have metallic bonding relatively well described, let's take a look at another type of bond, which arises from intermolecular forces between dipoles.
You mean like those between two polar molecules?
Yeah, polar molecules certainly possess dipoles, but let's start by taking a look at two nonpolar molecules first.
But nonpolar molecules don't have dipoles. How can they interact?
Well, you're right in a sense that they don't have dipoles, but it's their time average dipoles that are zero.
So then random quantum fluctuations could generate a spontaneous dipole at some time t?
Correct.
Then that dipole could generate an electric field, which would be proportional to the first atom's dipole over the distance between the two atoms cubed. Our second atom would then feel this electric field, and a dipole proportional to that E field would be induced.
Exactly, and we can describe the energy of this interaction as the product of the dipoles over the distance between them to the sixth power, which is derived in Griffith's C&M book on page 165. So taking the dipole induced at the second atom and plugging it back into here, we have an expression for the energy interaction in terms of the first spontaneously formed dipole squared.
So earlier when we thought about the time averaged part of dipole 1, we said it was 0. But the time average of the dipole squared is not 0.
No, it's not, which means that the energy of this interaction is also non-zero.
And that's all from spontaneous quantum fluctuations?
Indeed, and we call this the London dispersion force, which forms what we call van der Waals bonds. It's the most spontaneous and general of all dipole-dipole interactions.
So this type of bond occurs in every interaction, but we don't see it because other types of bonding like covalent or ionic bonding are at a much higher energy and overshadow the van der Waals bonds. Additionally, the distance term in the denominator seems to imply this interaction won't occur unless the atoms are extremely close to one another.
Right. These interactions also exist in various combinations of polar and nonpolar molecules.
Oh, okay, hold on. I'm getting a little confused. Let's put everything in a table. That's much better. We won't bore you with going through every interaction here, but it would be good to keep this table in mind.
One of the most important of these is the hydrogen bond. As an example, let's take a look at a strand of DNA. Where do you see this dipole interaction?
Well, in the middle of the DNA strand, you have this pattern of oxygen, nitrogen, and hydrogen. And on the one side here, nitrogen is pulling hydrogen's electron further from the hydrogen, which leaves it electropositive. And with oxygen slightly electronegative, a force develops between the two dipoles, holding our DNA together.
So here's a fun one. You can also take a look at this interaction in terms of its temperature dependence. So we know that this force in DNA is strong enough to hold it together at room temperature. If not, we'd be in trouble. On the other hand, when you start cooking an egg, what happens when we turn up the heat?
So the heat is going to start breaking some of the lower energy interactions, such as our van der Waals bonds. The proteins in the egg white will then have to reconfigure themselves into new structures, which give the cooked egg its white color. But that didn't take much temperature as opposed to melting something like silicon, which is based off of covalent bonding.
Okay, this looks like a good point to recap. Today we introduced metallic bonding, specifically approximating the electrons as a particle in a box, and thus a delocalized gas.
Then we looked at various types of dipole and or induced dipole interactions, their relative strengths, and how nonpolar molecules can bond through spontaneous dipoles formed from quantum fluctuations as in the London dispersion force.
As always, here are some questions to ponder. First, how would one identify van der Waals bonds experimentally? Another one, how do geckos walk on walls?
And thinking about metals, how could one explain how they permanently deform, and why do certain metals like gallium have particularly low melting points?
Okay, folks, thanks for watching Solid State Physics in a Nutshell. Next week, we're going to take a look at various crystal structures and different methods of visualizing them. See you next time.